All right, so we've talked about, first of all, we've talked about momentum, okay? And if you remember, we talked about momentum being P equals mv. It's kind of like the oomph that something has, okay? But of course, we know that that changes, okay? We know that a bowling ball doesn't keep rolling forever and ever because it's going to hit something. Something's going to apply a force. Something's going to change its motion. Some sort of outside force is going to change that momentum. And that is what impulse is. Okay? That's the section for today. So, impulse, what is it? Okay, first of all, it is defined as the change in momentum. It's how much the momentum changes. Okay? So, do physicists like to write change in momentum out? Heck no. What they do is they replace change in with a delta and momentum with a p, and so you can just abbreviate it as delta p. Nice and easy. Okay. Now, there are two things about this. Number one, in order to change something's momentum or change something's velocity, right, what do you have to do? Well, you have to apply a force, okay? And you're going to, whenever you apply that force, you're going to be applying it for a certain amount of time. If it's quick, it's a very short time, but it is time. Maybe it's slow where you sort of push on something for a long period of time, okay? But the idea here is that change in momentum is produced by a force being applied over a period of time. So based on that, we could say that change in momentum equals the force that you apply times the time that you apply it, which shows us that the harder you push, the more momentum it's going to get, or the more the momentum is going to change. If you're pushing in the same direction as motion, then it'll speed up. If you're pushing opposite of the direction of motion, it's going to slow down. But the more you push, the harder you push, the more that's going to change. Also, the longer the period of time that you push, the more the momentum will change. Okay? We'll get to some more applications of that soon. Okay? So that's why impulse, you can define it as delta P. You can define impulse as Ft. You can even switch it to m delta V. Okay? This goes back to Newton's second law. Remember we said F equals ma, right? Well, remember we said that we could substitute in, we could say F equals m times delta V over t, right? Because acceleration is just how much the velocity changes over time. So we can substitute that in. Well, guess what? This t looks kind of ugly down here. This side is divided by t. So let's multiply both sides by t. And we get that Ft equals m delta v. And we just said that Ft equals the change in momentum. Okay? So that's why impulse and momentum, this is why we talk about it with Newton's second and third law, really with Newton's laws, because it all connects. You've got the change in momentum is the force times the time, which is literally just the mass times the change in velocity. So however much the velocity changes, okay, multiply that by the mass, and that is the impulse. So what you want to write down is that impulse equals change in momentum, which equals delta P, which equals F times T, which equals mass times delta V. They're all equal to each other. Just remember, impulse is change in momentum. Change in momentum. Just like acceleration is the change in velocity, impulse, which we don't have an abbreviation for, is just the change in momentum. It's the same idea. Okay, so let's talk about some equations here. We just said that all of these things are equal to each other. So what can we say? Well, one thing that we can do is we can say that, well, delta P equals F times T. And that's this one right here. That's an essential equation. Write that down on your essential equation sheet right now. Okay? The other way we could go with this is, we change that up, we could say that delta P equals m times the change in velocity. That's this one right here. Write that down in your essential equation sheet now. Pause me, write that down. A third thing we can do is we can say that F times T equals m delta V. It's all the same thing. You're just kind of setting it up three different ways. And of course, when you do this, you've got different flavors as well. In this case, if you divide both sides by T, you get that F equals delta P over time. Okay? Or maybe you want to divide both sides by F, and you get that time equals the delta P over F. So you've got this, if you know any two of these, if you know the change in momentum or the force, you can figure out the time. If you know the delta P, the change in momentum and the time, you can figure out what the force was. That's the idea. Right? Same thing over here. The change in momentum or the impulse is the mass times delta V. Well, what if you don't know the mass and you need it in the mass flavor? Well, you got to isolate the m and you get minus delta V. So you take the impulse divided by the change in velocity. Okay, what if you want to know the change in velocity? You want to know this guy right here. What do? Well, you divide both sides by m and you get that, let me redo that. The velocity changed by however much the momentum was changed divided by how massive it is. And of course, let's move on more quickly. Over here, well, there's lots of different flavors to that. But the idea here is that the force that you apply times the time that you apply it is equal to the mass of the object and the change in velocity. They're all dependent. Okay? All right. So let's talk units real quick. What are the units for impulse? Well, it's really just, well, let me show you. Okay, if mass is measured in kilograms and change in velocity, what is velocity measured in? Meters per second. So wait, it's really just kilogram meters per second. It's just the same as the momentum units. Absolutely. It's just momentum. It's how much the momentum changed. It's just like saying, well, if velocity is measured in meters per second, change in velocity is also measured in meters per second. So if momentum is measured in kilogram meters per second, change in momentum is also measured in kilogram meters per second. There is another unit that you can use, which is also simpler. Check this out. We also defined impulse as force times time. And the units for force are newtons. And that's multiplied by the unit for time. What do we use for time? Seconds. So you can actually use either Newton seconds or kilogram meters per second. That's up to you. I can't mark it wrong if you have one or the other. So just use whichever one you know you will remember and use. And don't forget, if you forget, use the equation. You know the units for force, you know the units for time, or you know the units for mass, and you know the units for velocity. So you can do this. Okay? All right. So what is the relationship between these two? Okay, between time, force, and impulse? Well, here's the idea. When you have a force, okay, that's applied for a long period of time, you're going to get a very big impulse. But when you have a shorter or smaller force that's applied for a shorter period of time, you're not going to get as much impulse. Okay? That's something you want to think about and write down on your sheet. Also, mass, velocity, and impulse. Okay? If your velocity changes a lot, you have a big impulse. Your momentum changes a lot. Okay? Also, the less massive the object is, let's say you have two objects, a bowling ball and a baseball, and you get them up to the same speed. Which one required more impulse? Which one changed its momentum the most? Well, the change in velocity is the same. The mass is different. So the baseball had less impulse. You had to impart less momentum to it than the bowling ball. You had to give the bowling ball a lot more momentum because it was more massive. Okay? Last little bit here. Okay? Okay? You've got applications of impulse. Right here, if we're talking about impulse, delta P equals F times T. What does this mean to us in the real world? Safety. Safety, safety. Okay? This is the number one thing to think about in safety. Let's think about it simply. Let's say you jump off of your bed. You can either have a soft landing or a hard landing. Okay? So if you jump off of your bed, okay, and you land in a big pile of foam, okay? Just a big pile of foam, you fall in, it's a nice soft landing. What's happening there is you are falling, okay, I'm going to assume you're a sphere. You're falling and you have a certain amount of momentum. I don't know, just for numbers to help you out. Let's just say you have 10 units of momentum, okay? Now, in the hard landing, let's say you jump off the bed and you get about 10 units of momentum as well. So same thing. Now here, you're going to have a soft landing where you have some foam. It's nice deep foam, and you go in, you fall, you hit it, and then you sort of sink in and you get down here. And so it's just nice soft landing. I don't know if that drawing helps you at all, but let's pretend it did. Okay? Whereas here in the hard landing, you're basically hitting the solid floor and stopping very, very quickly. So you just go stop, right? Here, at the end, your momentum is 0. Same thing here. At the end, your momentum is 0. The difference here is how you got there. In a soft landing, let's go with a hard landing. In the hard landing, okay, remember, your change in momentum in both of these is -10. But here, you had a very small amount of time in which this force was imparted. Let's say it was just 1/10 of a second. Okay? So we could even say time equals 0.1 seconds. You had to have a big force on you in order to stop you. In fact, if we calculate this out, okay, if the change in momentum is force times time, okay, and that means that it equals the force times 0.1, okay, and you divide both sides by 0.1, guess what? Your force over here, your force was 100 newtons. It's a 100 Newton force, okay, over 0.1 seconds. 100 Newton force over 0.1 seconds. Big force, small time, okay? Whereas on the soft landing, it's a lot nicer, okay? On the soft landing, you actually, because you're touching and you're slowing down a whole lot less quickly, okay? Let's say in this case, the time is, let's say, half a second, okay? If the time is half a second, what's your force going to be? We'll say it's a long time, but a small force. Let's do the same equation. Okay, if delta P equals force times time, okay, I'll do it a little differently this time. Let's solve first. Divide by t, so we know that we're going to cancel out the t's. So for the force equals the change in momentum over t. These are all essential equations that you have on your paper right now, so you don't need to redo this every time. But so the change in momentum was -10 divided by 0.5. And what do you get? 10 divided by 0.5 is -20 newtons right here. So force equals -20 newtons. And mistake here, I forgot my negative. That should be negative. I forgot that. That's a -100 Newton force. But the idea here, ladies and gentlemen, is that you have, right here, a -20 Newton force, and here it's a -100 Newton force. Hard landings give you big forces over small periods of time. Soft landings give you a smaller force over a longer period of time. Okay. I might have to put this on another one, but let's do an example. Okay. Find the impulse of a bowling ball that is pushed for a time of half a second with a rightward force of 50 newtons. All right, so what do we know? We know that it's pushed for a time of 0.5 seconds. We also know that it had a force of 50 newtons. Those would be our givens. Okay? Now the question is to find the impulse. We are looking for impulse. So we write delta P equals question mark. All right. So if we go back to our essential equation sheet, or if I just look down here because I put it on the slide, we know that we need to find the change in momentum, the impulse, and that equals force times time. Okay? So let's start plugging and chugging. Substitute and solve. So you've got 50 newtons times 0.5 seconds. Okay? If you plug that into your calculator, what do you get? Well, the 50 times the 0.5 is the same as 50 divided by 2. So that's 25. And what do we do with the units? Well, we just multiply them together. So it's 25 Newton seconds. That's how much the momentum changed. Okay? You, or whoever pushed this, gave it 25 Newton seconds of momentum. Okay? Now the second part of this question, though, asks, if the bowling ball was started at rest, what is the final speed? So here's what we do. We know it started at rest, so just to kind of, let's see, our initial velocity is 0. Okay. What is the final speed? Okay, we're looking for the final velocity. Okay. And we know that the mass of the bowling ball is 5 kilograms, so we know the mass is 5 kilograms. What else do we know, though? Aha. We know that the impulse, or the change in momentum that it experienced, was 25 Newton seconds. So that gives us an advantage here because we know, if we look at this essential equation right here, that the change, how much the momentum changed, the impulse equals the mass times the change in velocity. So the idea is we know this. We know this. It's right here. So we can calculate this. Now if you look back at your essential equations, or if you just figure it out, delta V equals the change in momentum divided by the mass. So we just substitute and solve. And so the change in momentum was 25 Newton seconds. And you divide that by the mass of 5 kilograms. And what do you get? Well, 25 divided by 5 is 5. And now you could leave it as Newton seconds divided by kilograms. Okay? But we all know that velocity is measured in meters per second. And you have your answer there. Okay? All right, that's it for applications of impulse and how impulse works. If you have any questions, let me know in class.